Um, the next team, which was tasked again with removing the mercury, but using more conventional wastewater treatment methods. So specifically evaluating some of the newer innovations in filtration technology that are out there to see if this would be feasible. So with that, let's turn it over to Team.
So we are team 3, EnviroDream. We designed a filtration system to remove the mercury from Hamel Creek. I am Josh.
I'm Kyle.
I am Teresa.
And Victor.
And I'm Victor.
Victor.
Oh, there we go. Sorry, the slides are lagging a little bit. All right, so the broad scope of our project was to devise an effective filtration system to remove the mercury from the mine discharge. Within that broad scope, there were a lot of smaller objectives that needed to be considered, or I guess larger, even some of them. We had to analyze different treatment methods, while also being wary of what constituents are inadvertently removed by whichever treatment we choose for a given task. Construction site planning, interruptions to any wildlife while doing that, and then I guess being aware of our space constraints on that site. Sustainable management of the byproducts of our water treatment system. Cost estimating, scheduling, any permit requirements that might pop up. And then we had to do some analyses on impact of the construction.
Yeah, so as Victor was saying, pretty much our main objective, however, was to identify the viable treatment options to remove the mercury to the level of the TMDL required. So we initially looked at some of the more conventionally used treatment technologies, such as adsorption, which uses granular activated carbon, ion exchange, membrane filtration, of which we specifically were looking at reverse osmosis, and then finally we also looked at chemical precipitation. So right away we were faced with the challenge that our initial mercury levels are already extremely low, so a lot of treatment technologies are not able to hit that final low level of mercury that we require. So that was our main parameter, is that treatment efficacy. But we also wanted to look at the operation and maintenance, because we are constructing this in the middle of the TML, and there are 4 seasons, so those are some difficulties there. As well as we also wanted to examine the cost and the power requirements with that sustainability view. How much energy is the system going to require? So with these parameters in mind, we determined that membrane filtration, specifically reverse osmosis, would be our only treatment technology where we could have a high guarantee of actually reaching that treatment level required of the mercury. However, once we chose this method, we spoke with Dr. Urban and some other engineering professionals who suggested that instead of just relying solely on a very energy intensive and costly method, we could implement a series of treatments. So with this in mind, we had found a really awesome study about the use of an alum coagulant called Ultron for a stream out in California that had very similar aspects to our stream here in the TML. And with that in mind, we determined that starting with the chemical precipitation step and then following it by reverse osmosis would be the best treatment technology.
So with that said, you can see here, we started with a detention basin to keep a constant flow in the system. Then that moves to coagulation and flocculation. And this waste moves to the filter press to be treated. The rest of the water that's cleaned, or more cleaned, let's say, goes to the reverse osmosis treatment system. This is where we're polishing off the mercury that is still in the water. The coagulant in the flocculation is supposed to do approximately 80% of the mercury removal, and the reverse osmosis was expected to do about 19%. And then from there, it goes to the discharge basin to be replenished into the creek. So here's a top view of what I just presented. We have the water coming in from the mine discharge outlet into the detention basin, which is quite large. And then from the detention basin, the water travels to the treatment building where the RO unit and the coagulation and flocculation are conducted. And then from there, as well as the filter press. And then from there, from the building, it moves to the discharge basin to go back into the stream.
So as Josh went over, our first step in our process is the chemical precipitation. So we're going to add our alum coagulant ultron before it actually enters the flocculation basin. That's going to be inserted with an inline static mixer. So then once we have that alum in, it enters the flocculation basin where it has large vertical pitch bladed turbines that are going to mix in that coagulant to form floc. Floc is formed because of that reaction between the coagulant and then the constituents in the water to form particles, and preferably with a lot of mercury in them. Because then once the mixing occurs in the flocculation tanks, it's going to go through a diffuser wall into the sedimentation tank. So the sedimentation tank we calculated to be approximately 14 meters long. This is calculated because of the size of the floc particles. It will take approximately that long for the particles to settle all the way down to the bottom of the tank. At the bottom of the sedimentation tank, we have chain and flight collectors that are going to push the sludge along the bottom to be collected at the sludge hopper, which will then pump that sludge out of the tank into towards the residual treatment, which is our belt filter press. We're going to touch on that a little bit later, but basically the belt filter press is just going to squeeze out excess water, and that excess water is going to circle back into the start of this treatment process. And also, as you can see, we have 2 of each, and this is just for treatment redundancy. And also at the end, we have overflow meters that take that clean effluent water that is going to be piped to the next treatment process, the reverse osmosis.
So with the reverse osmosis, most of the calculations were based on the feed flow and the feed concentration in table 7. The feed flow is a bit of an estimation. It's about 1/3 of the 2.5 cubic feet per second that we had initially in 2002 when they measured the flow. However, we went to the site and we determined that this is not the flow. So we used about 1/3, and then we had a safety factor on top of that. The feed concentration is based on the initial 130 nanograms per liter that we designed for. This is 20% because we estimated that the coagulation and flocculation would treat about 80% of the mercury. So the permeate flow and concentration, the concentrate flow and concentration are both calculated based on the feed flow and feed concentration. And then in table 6, we have the rejection and recovery. The recovery was 40% to keep the costs a little bit lower than a high recovery system. And the membrane area was 90 meters squared because we needed to treat a large flow of water. And then we have the channel height, element length, the temperature that we'll be operating at, flow area, and then we need 15 elements. And what elements are just big cylindrical tubes that treat the water in the reverse osmosis system that have the membranes.
As with any water treatment removal process, there's going to be some buildup at the filter with debris. So as the filters will be periodically cleaned, so the waste sludge will be taken and set through the belt filter process and dewatered to increase the solids content per volume, which will result in solid cakes, which have a lot less water per volume, which makes it easier to transport and handle and a lot more efficient than that. The belt filter press process is it's a large component of the sustainability aspects that I researched, which are on the next slide. So the sludge that is expected to have a very small amount of mercury concentration from the dry weight of the sludge, which means that it can be reused sustainably in other processes. Those other processes include coagulation, or as the coagulant or the coagulation flocculation process of other water treatment processes, and absorbent in the granulation process. It can also be used as a complementary ingredient to concrete brick production, to fly ash. And in the experiments that we found in our full report, the bricks that were made with the recycled sludge had comparable compressive strength to the regularly produced concrete bricks. So it's a viable option to reuse those there and not lose any strength characteristics in the concrete blocks. That being said, if the concentration does happen to get too high at any point, the mercury in the sludge must be landfilled in a specially designed landfill that is lined to prevent any mercury seepage into the environment.
So we've gone over our design, but outside of that, we also wanted to analyze the impacts that this treatment system would have on the environment and the community, the different stakeholders in this community. So first and foremost, this is going to be beneficial environmentally. The other groups have gone over some of the issues with mercury itself. Since Camel Creek is draining down into Torch Lake, there has been a lot of bioaccumulation of mercury in the wildlife, specifically fish in that lake. So remediation of Camel Creek using this treatment and filtration process is going to help prevent further bioaccumulation, getting value back recreationally and environmentally to the area. But on the reverse side, our choice of treatment technology, specifically the reverse osmosis, is very energy intensive. Currently, our design calls for energy just being purchased from the local electrical facilities, which use natural gas for most of their energy production. So for future determination of maybe better sustainability, we could look into more renewable energy use. But currently, we just have a lot of energy requirements to hit our treatment standard. Also, this is a historical site. This was where an old mine was in the copper country. So to attest to that, we considered adding like some sort of plaque or maybe dedication of the treatment facility in remembrance of this historical significance. In addition, as the first group mentioned, this area is surrounded by wetlands, so we do have to consider some different permits because we will be constructing and discharging back into an environment that has wetlands.
So assuming we get those permits, the project we estimated to cost around $1.5 million. And the operating and maintenance costs are about $200,000 a year, which is a little steep. The big ticket items for construction in our estimate break down like this. So we have our mobilization, which is capped at 5% of the total cost of construction. We have the basins, both of them together, account for about 8% of the total construction costs. The RO system and the chemical precipitation system together are more than half of the cost of the entire project. And then we have the engineering contingency fees, which are about 27.5%. And then we have 2.5% left of just surveying, soil boring, erosion control, site preparation, and then whatever other small items might pop up. All these unit prices for the estimate came from RS means data, except for our two treatment systems, the RO and the coagulation tanks. Those came from a separate sheet, a spreadsheet that the EPA created.
Victor, are you still there?
Can you hear me?
Yep.
Oh, okay.
I had cut off before engineering fees.
Before it?
Yeah, like we haven't heard you say that.
All right, so the engineering fees and contingency account for 27.5% of the entire cost of the project. All these costs came from RS means. And overall, we estimated it'll take about 45 days for the construction, which seems about right. So we did have some challenges. The project itself is super diverse in its tasks and solutions, and that's a good thing and a bad thing, I guess. But some of the challenges that we found specifically related to the scope being so broad, and creating an entire filtration system is kind of a big task to undertake in only a few months. So as a result, our design sort of turned more into a feasibility study toward the end. Another issue is that the flow data is inconsistent in that we don't have an entire year of flow data. We only have flow data for one part of the year. So it created a lot of uncertainty in our treatment system design as a result. And lastly, we have estimating unit costs for non-standard items such as the RO and the chemical precipitation system was difficult just because there's not a good standard resource that's been made to use. And in conclusion, the cost of the construction is high, but the operation and maintenance being $200,000 a year every year might be a little excessive over the life of the site and of the contamination. In addition, we need a pilot scale test to prove that we can successfully filter out all of the mercury. In addition to that, it's highly energy intensive. So operating costs, energy intensity, and all that to not be entirely sure that it's going to work is not ideal. But it does have promise, and we think it could be effective if the pilot scale testing is conducted appropriately.
So we would like to thank Dr. Urban and Eric Mundell, PE with Hillcorp Alaska, for all their guidance and their help along this process. Any questions? Yep.
Yeah, so I have a couple of questions that are related, and I probably missed it, and we did talk about it. The flow, what was the flowing design for coagulation, population unit?
So the flow we used. So we used, here, we'll go back here.
I think it was 1.5 feet per second.
Yep, and that converted to 0.8.
Because my big question
Or-
is flow, but it has to do with redundancy. And that you pretty much use reverse osmosis as a redundant unit for chemical precipitation. And so then wondering, could you reduce your cost, both construction and then operation maintenance, by just having one unit, which might make it easier to operate, knowing that your flow is could be very low and it's going to be very seasonal. So that's my first question. And my second question, we didn't talk much about it, is that you had a discharge tank, discharge basin. I really wasn't sure what purpose that served. So maybe you could address this.
Sure. So, well, the first question, yeah.
I mean, we really like carbon science our stuff. So if with the variable flow stuff, it really is flexible. Like we use the third of what the TNPL said. So like theoretically, they do have those tactical rates. You could just like triple the size or make it smaller. And unfortunately, like we did think that the RO would be necessary because our conservative estimate using just the chemical precipitation was only 8% removable on mercury. So like the TMDL is very serious, like the RO is necessary, but like because we do have two treatment options and it's pretty flexible, the low flows really well, maybe we just use
Or in the event that something broke, right?
Yeah,
I mean, we
exactly.
design for redundancy typically for treated water or wastewater, because for water, people don't like oil notices. And second, we have wastewater, we really don't want to tell the state agency, we can't be permanent, right? But in this case, you have that redundant system that might reduce your costs.
Yeah, and we found that we were looking into GAC as well, and it was like varying between 50 and 99% removal. So we were like we were not confident going in with just one operation.
And then the basin at the end, what's its purpose?
So the main purpose was just to have a constant flow back into the stream from the RO. And the RO system's a bit smaller than the coagulation and flocculation tanks. So we didn't know any other way to move the water from the RO like directly into the stream from the building.
I'm just wondering if your flow is so variable at the end, would that basin be more useful at the beginning of the process so that you can control the flow in?
Yeah,
We do have a basin, detention basin in Porter.
we were thinking it was going to be the same flow all the way through, which is why we kind of had two basins.
Yeah, because like part of it was like, you don't wanna just, I guess, I think our initial thought was like, you don't wanna just be putting a ton of water in the stream flow, like having that basin and gives us a little more variability to, like based on what the stream flow is.
Control the flow.
Yeah.
Yeah, definitely.
Other questions?
Could you go back to the schematic that shows the layout of the whole system? So how, I'm just wondering if you're going to have like stratification or short circuiting of the flow in your detention basin. So are you going to have settling of the particles that have mercury on them? Is that a good flow design for your detention basin?
That's a good question. I think the main thing, is with the nanograms per liter for the mercury, we figured that there would not be a lot of accumulation in the basin, but that is certainly something we should look into as a recommendation if we were to move forward with the design, like cleaning.
Our choice of layout primarily was just because it was close to the discharge point, and just like all in this little area. We could keep things close together for easy construction. So something to consider.
Questions? Any questions online? Well, thank you.
We've actually got schedule, so.